Welcome back, everybody. Welcome back, those of you watching online. It's a pleasure for me to introduce our next speaker, a local, Yael Karshon, who's going to talk to us about integrating vector fields over subcartesian spaces. Subcartesian.
Yep.
Sounds jazzy. Welcome.
Thank you, Tony. And thank you to the organizers, Lisa, Taras, and John Beck, for the opportunity to speak here. What I'm talking about is not toric topology, but it is a tool, a technical tool that I hope might be useful for topologists who might want to venture into the C infinity world. So at least when we talk about manifolds, integrating a vector field, going from a vector field to a flow, is an absolutely central tool, not just for dynamics, but also in differential topology. If you want to do connected sums of manifolds and you want to prove that this is well-defined up to diffeomorphisms, eventually you will need color neighborhoods. You will need to use to integrate vector fields eventually. For the students, I highly recommend the book by Brecker and Yannick about differential topology, which illustrates the details for how to use integration of vector fields to do stuff with manifolds in the differential topology context. And subcartesian spaces are more general than manifolds. So this talk is about going from vector fields to flows for these more general spaces. So we can describe manifolds informally as smooth spaces locally modeled on open subsets of Cartesian spaces. A Cartesian space is just Rn for some m. And we can describe subcartesian spaces as smooth spaces that are locally modeled on arbitrary subsets of Rn. So we know what the local models look like, but then what do we mean by smooth space? And this has more than one answer. And I personally, when dealing with objects that are more general with manifolds, I personally like very, very, very much two different approaches that are very elementary and are a lot of fun. And each of these approaches, there's some interesting question because it's so elementary and simple, like, okay, to what extent does this simple elementary approach reflect what we might be interested in? How far can you get with the elementary approach? I kind of really like to try and take the elementary stuff as far as possible. And only one of these two elementary approaches will be suitable for us today. But to put things in context, I will at least mention both of them and then ignore one of them and continue with the other. Is this visible all the way to the bottom? More or less up to here? Okay, this might be enough. Okay. So I'm going to give you two different answers to the question of what is a smooth space. And the first one is the one we will deal with today. And the second one is just for the context. It's not for today. So the first answer is a notion of a differential space. And unfortunately, there's many definitions with the same name. And I'm thinking of a structure that was axiomatized by Sikorsky. And there's a book about these, specifically subcartesian spaces, written by Schnetitsky. And you might tell from the names that this is sort of a popular among mathematicians of Polish origin. And the second structure is a notion of, the one that we will not deal with today, is a notion of a diffeology that is due to Jean-Marie Suryaw. And there's a nice book about these written by Patrick Iglesias-Semmer. A differential space is a set equipped with a collection of functions from the set 2R. This collection is required to be non-empty and to satisfy three axioms that I will write in a moment. And we think about this as the smooth functions on M, providing us with the smooth structure. Many of us often think about a sheaf of functions, but in fact, in this, we are in a smooth context, C infinity context. We have bump functions. And thanks to bump functions in this context, you can recover everything from the global smooth functions. And the theology, which I'm not talking about today, is you're equipping your space with a collection of maps to the space that are declared to be the smooth maps to the space, whose domains are open subsets of Cartesian spaces and can vary. And
Yael, master question.
hold on, this collection is again required to satisfy a small number of axioms, and I'm not talking about this today. Yes.
What do the words locally modeled on mean?
I will explain. I will explain. Informally, little pieces of your space look like little pieces of either open subsets of Rn or arbitrary subsets, but this is informal. So I did explain space, except I did not write the axioms, and I still need to explain locally modeled. So the version that I will take today is that my set will be equipped with a topology but the very first axiom will be that the given topology coincides with the initial topology, namely with the smallest topology for which all the functions in our set fractor F are continuous. So I could have just ignored the topology and just declared that, equip the space with the initial topology and move on. The second axiom is the one that sees the C infinity structure. The collection of maps has to be closed under composition with smooth maps. So if we have little f1 through little fm in the collection, and we compose it with a smooth map to Rn, then the composition is in the collection. And the third axiom is locality. Determining whether a mystery function is in the collection, to determine that, it is enough to examine it locally. So given a mystery function, if each point has an open neighborhood, and now I'm using the topology on M, which coincides with the initial topology. And has a function in the given collection that coincides with the mystery function on that neighborhood, then the mystery function is also in our collection. That's the last axiom. I think both of these are more or less 1980. And as soon as we have the notion of a differential structure, there's a very natural notion of a smooth map. If you have two differential spaces, a smooth map is just a map of sets such that the pullback of any or the precomposition of any smooth map on Y is a smooth map on X. Smooth map in the sense of belonging to the given family. And diffeomorphism in the sense of differential spaces simply means that the map is bijective, and both it and its inverse are smooth. Of course, every smooth manifold has a natural differential structure. In particular, Rn has a natural differential structure. And just very quickly, let me note here that when I say real valued smooth function, this is not ambiguous. In fact, a little lemma or exercise with these definitions. If you take a differential space and you take of all the smooth maps from it to R, where R is equipped with its natural differential structure, that's the same thing as the given collection of functions that was a priori attached to the differential space. So the notion of smooth map is not ambiguous here. Now, I would like to say, so now I have a notion of diffeomorphism locally modeled for Tony should be every point in the space has a neighborhood that is diffeomorphic to an arbitrary subset of some Cartesian space. But then I need for this, we need to be able to pass to open subsets of the space or to arbitrary subsets of Rn. And we can do that because we have a notion of subspace. If we have a differential space and then a subset, any subset, in particular open subset, the subspace differential structure that we put on it is defined to be the set of all functions, real valued functions that locally extend. So each point on the subspace, there exists a neighborhood W in the ambient space, and there exists a function in the ambient differential structure that coincides with our given function on the intersection of the subspace with the open set. And the initial topology does coincide with the subspace topology in this case. And maybe I will mention, since I mentioned subspaces, maybe I will mention quotients. If you have a compact group acting on a manifold, you can take on the quotient, you can take the space of smooth functions whose pullback is smooth. And this is a differential space. This is a differential structure. It satisfies the axioms. And we have here the quotient topology. And previously, we have the subspace topology. Now, one has to be careful. Of course, this definition makes sense whenever we have an equivalence relation on a differential space. But if we are not careful, we will obtain usually the collection of functions whose pullback is smooth upstairs. Usually that collection, in general, the initial topology for that collection might not be the same as the quotient topology. And one does work with these, and then one takes the initial topology and not the quotient topology. But in the cases that we care about, which are quotients by compact group action, because of the ability to average, the initial topology really does coincide with the quotient topology. This is the special case I will be interested in. Yeah.
What is playing the role of V? The V up there. What is the V referred to in this explanation?
The V?
The V in your depth, right?
I've not yet. You're rushing. You're rushing. So at this point, I can define a subcartesian space. Now the V will come about, okay? So you don't have not to keep Tony in suspense. So a subcartesian space is a differential, again, for the students here. For me, when I see a new piece of mathematics, for me personally, it is extremely important to understand, am I being given a new piece of structure, or am I being given a new assumption or axiom? For me, that distinction is really crucial. So for subcartesian space, this is not another structure. This is just another axiom. It's a property of a differential space. So a differential space is subcartesian if and only if it is locally modeled on arbitrary subset of Cartesian spaces in the following sense. For each point in M, there exists a neighborhood U. If you wish, open neighborhood with respect to the given topology of M. And this neighborhood is diffeomorphic to some arbitrary subset of Rn. Now, N and V can differ. So if I should say, I would say there exists an N and, oh, I'm sorry, let's say here. There exists an N and there exists a V in Rn such that, etc. They can depend on the point. The dimension at the point will be the smallest possible such N, and the dimension can vary from point to point. For example, We can take the rationals inside the real numbers. You don't have any continuous curves there, but the topology somehow sees this is not discrete, and the smooth structure also sees Q in a sense. So this is one-dimensional. It means diffeomorphic in the sense of differential spaces, induces a bijection between the collections of smooth functions, where smooth functions means on each one separately. Here, the smooth functions are induced from M. Here, the smooth functions are induced from Rn. And in any case, smooth means locally extends. So you're sort of building up the definition.
Do you have an example where P is the sort of space-filling curve or something?
You can have, well, by definition, a space-filling curve as a set is all of R2 or the whole cube. So you're not going to see the one-dimensional structure. So you're really seeing the structure that you're seeing. It does not remember a parametrization. It's a subset of Rn. Everything is coming from the ambient Rn. Okay, this is, you might want to examine technology, but this is not what we're doing today. So actual subset. So a manifold is a differential space, manifold with boundary, manifold with corners. The notion of a smooth map between manifolds or manifold with boundary, etc., is the same, equivalent to the usual notion. We can take a disk inside R2. That's an example of a manifold with boundary. We can take the union of X and Y axes inside R2. This is two-dimensional at the origin and one-dimensional elsewhere. Maybe a little anecdote. I mentioned that this work is mostly with Eugene Lerman. And this has a bit of a history, but at the end of the day, there's two papers, one joint with him that is published, and another which is my paper, but he has contributed quite a bit to it. And he preferred to not be a co-author for a couple of reasons. One of them, that paper, which is what I'm talking about today, is more general. But for his purposes, he just needed the cases that we had in the first paper. And the second paper is more technical, and there's pieces that are surprisingly subtle and somewhat disturbing how subtle they are. And one can ask, well, to what extent is this second paper more general than the first paper? And this has to do with the following anecdote. Well, subcartesian spaces do often admit Whitney embedding. So what I mean when I say Whitney embedding, if I have a subcartesian space, I can ask, is it diffeomorphic to a subset of some big Cartesian space? Definitely, we have some necessary conditions. In order to do that, M has to be finite dimensional. And it has to be second countable. But if you have a finite dimensional second countable subcartesian space, does it admit an embedding in a big Cartesian space? Yes. 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 And in fact, a necessary condition from being embeddable is for it to be subcartesian. That's definitely necessary, because if it is diffeomorphic to a subset, then definitely it's local. So that is definitely, thank you. So these are necessary conditions, but then are these conditions sufficient? Because and that's sort of an interesting question. if you also assume that the subcartesian space is locally compact, then definitely these conditions are sufficient. And I know two proofs. I'm aware of two different proofs. And both of them should, yeah. I can give references when they're sketched. One of them might have problems, but basically I'm confident, zero doubt, that's fine. Now, in the general case, in my paper with Eugene, we do quote a paper where they claim that these are always embeddable, but that paper has a proof which is flawed, and it might be fixable, but I'm not sure. And that paper, they say, well, actually, they say it's not our proof. We're just simplifying someone else's proof. But if you go to that someone else's paper, you're not finding a proof. And there's a bunch of papers from all from the late 70s where each person says that the other person had already done it. So I'm not very clear on the status of the literature on that. So although we do quote, it's definitely claimed. That these conditions are sufficient, but I don't know a correct proof in the literature. So, maybe it's easily correctable, the one I know, but I don't know. I'm not sure. So that's an interesting question. Actually, I'm just just about to start an undergrad project, which I hope might help clarify some of this. But of course, there's also interesting cases that do not satisfy the necessary conditions. For example, maybe I'll give another example. Do I want to say this? If you have a compact Lie group acting smoothly on a manifold, the quotient space is in fact subcartesian. And this is a consequence of a few things. We've got Koszul's slice theorem that identifies little neighborhood of tubular neighborhood of an orbit with a certain associated bundle. And it identifies the quotient with the linear quotient of a vector space by a compact Lie group. And that linear quotient, by a combination of a theorem of Schwarz and of Hilbert-Basis theorem, can be embedded in a Cartesian space. But in fact, you can patch these things together. For example, if I had time, if I have extra time, I'll give you some details. But for example, there exists a connected S1 manifold where, well, at each point there's some dimension, but these dimensions can go up and up and up and up. Yes. Yes.
So for the compact action, do you have any constraint, like what kind of action it is? Like
Smooth.
any quotient will be
Smooth.
smooth. Oh,
Everything is smooth.
just smooth action, like
Yeah.
not free,
No.
nothing.
Yeah, I don't know what the right word is, that these the quotient. Oops. Yes, I'm not sure what the right word is, but that these quotients they have a Whitney stratification or something like this. They have locally a conical structure, right? And I think that should give you
The question is, what do
subcartesian.
you mean by conical? There's a certain
that
delicate,
some piece
there is a
is-
delicate
some-
interplay between the smooth structure and the topological structure. These quotients, if you take the decomposition of the manifold into orbit type strata, you get a decomposition of the quotient. If you view the quotient, now there is a notion of Whitney stratification. Usually that notion applies to subsets of manifolds, but it makes perfect sense to talk about that notion for subcartesian spaces. That's still, everything makes sense. And these quotients will be Whitney stratified. They will satisfy Whitney conditions A and B. this implies a certain locally conical behavior topologically, not smoothly. Smoothly, it's not quite a cone, but it's something else. And yeah.
Okay. Thanks.
But in fact, this is an opportunity to mention that this context of subcartesian spaces is very, very appropriate for handling stratified spaces. Whereas, yeah, although one has to be, and anyway, that's there's more to say about these. I've got a student that just wrote a very interesting paper in connection with that's a different story. There's subtleties. I mean, some people here might be familiar with stratified spaces, and there's a lot of subtleties. But yeah, but this is a kind of a good context. Yeah. Any other? Yeah.
What dimension of subcartesian space?
So by definition, yeah, by definition,
What is dimension of subcartesian space?
Yeah, no, excellent question. So let me actually, yeah. So what is the definition of dimension? So by definition, the dimension is the supremum over all points of the dimension of the space at the point. So then I need to say, what do I mean by the dimension space of the space at the point? And that will be the lowest dimension of a Cartesian space in which you can embed some small neighborhood of the point. And it turns out to coincide with the dimension of the so-called Zaritsky tangent at the point. Well, it embeds an R, but if you take a neighborhood of point, you will not be able to embed it in 0. So I'm not going to write that down. I said it verbally. So we want to talk about vector fields and flows. So what's a vector field? So for manifolds, there's a lot of different definitions which are equivalent to each other. And I will choose one of these definitions that works very well for subcartesian space, in fact, for differential spaces. And I will write down that definition. So these are maps. Little v stands for vector field that takes smooth functions to smooth functions that are linear and satisfy the Leibniz property. In case of a manifold, this turns out to be the same thing as a vector field. And we want to integrate that into a flow, and you construct the flow by assembling together the integral curves of the vector field. So what is an integral curve of a vector field? There's a map from the interval to M. And maybe I will already warn you in my first paper with Eugene, as well as in Schnetitsky's book, this map was required to be smooth in the sense of differential spaces. Right now, in this context, I'm not going to insist that it be smooth. This will be proved later. Turns out to be easier if we don't insist on that a priori. But so first of all, what is I? The domain of this I is an interval. What is an interval? Well, it's not empty. It's a connected, non-empty subset of R. So it can be all of R, it can be array, it can be an interval, but then it might contain the endpoint, it might not contain the endpoint, everything goes. And it can be a singleton. Turns out we have to allow singletons in this context. So then again, when you work with manifolds, often you look at the textbook, the domains of their integral curves are going to be open intervals. For us, we have to allow this bigger freedom. I will explain in a moment. And now there's two possibilities. Either I is a singleton, then we declare that a integral curve. Or if I is not a singleton, then you can evaluate the function along your curve. And this is now a real valued function on a non-degenerate interval, possibly with some endpoints. So you can ask, is this or is this not differentiable? Where at the endpoints, this would be left or right differentiability. And you insist that this be differentiable, that's the usual condition, and the derivative be given by the value, evaluating the vector field on your function at that particular point. So that is the usual definition for integral curve, except we are allowing singletons. Let's do some examples. Suppose that you're taking the rational numbers and v equals del x. This is a perfectly good vector field. It is non-zero, but all the integral curves are singletons. So you cannot recover the vector field from the integral curves. Well, these are maps from singletons to the space, actually. Let's take the two-dimensional disk inside R2. And again, v del x. So what are integral curves? Here, these are just horizontal curves that go to the right at speed 1. And here you can make, if you try to make them as big as you can, you end up with an integral curve whose domain is a closed interval. And at the top and bottom, the vector field is pointing out. So your integral curves are just singletons. You have to allow the singletons. Now, integral curves, as usual, are partially ordered by inclusion. An integral curve is included in another if its domain, if it is given from the other by restricting to a subinterval. And then we have the notion of maximal integral curve. Now, if you have a partially ordered set, there's a notion of a maximal element. This is an element that doesn't have guys that are strictly more than it. There's also the notion of a maximum, a guy that is bigger than all the others. And that's not, it implies maximal. It's not this. Okay. So this is maximal in the usual sense. It cannot be extended. So this is integral curve. Such that for any other integral curve, sigma from J to M, if sigma contains gamma, which means that J contains I and gamma equals sigma restricted to I, then in fact they're equal. So J is equal to I and gamma equals sigma. So that's the usual notion of maximal. And let me give you another example, which is kind of interesting. When you have a vector field on a manifold and you take all the maximal integral curves, they assemble into a flow. And the flow domain is a subset of the manifold cross R. The manifold coordinates is the initial condition, and then the R coordinate is the time evolution. And the domain of this, the flow domain is open. That's kind of very part of the fundamental theorem of flows for manifolds. And here you can have something more interesting. Let me again take del del x, but now my subset of R2 will be the x-axis. And this guy. So here, all the maximal integral curves, their domain are open intervals. On the x-axis, the domain is all of R. And above the x-axis, the domain is a bounded open interval. But near the origin, these domains of the maximum integral curves get smaller and smaller and smaller and smaller. You cannot find an epsilon where near the origin you will be able to find an integral curve defined on negative epsilon, epsilon in the whole neighborhood. So you don't have the usual existence theorem for integral curves of vector fields. Yeah, it's a little bit more subtle here. But now let me give you the statement of the main theorem on how the integral curves do assemble together into a flow. And here we have a subcartesian space and a vector field on it. Then, first of all, there exists a unique maximal flow. What is that maximal flow? It's a subset of M cross R together with a map from that subset to M. And the conditions under which it exists and is unique are such that for every point in the manifold, if you take the first coordinate to be that point and you vary the second coordinate, this is a map from a subset of R to your space. And this map will be a maximal integral curve. So this domain will be connected, is a maximal integral curve of phi with initial condition psi x0 equals x. In particular, the domain does contain the origin. And under these conditions, this guy exists and is unique. Same as for manifolds. Actually, how am I doing with time? Oh, I'm almost running out of time. At least I'll get the statement. Moreover, for every integral curve, this contains all integral curves. So for every integral curve of V with initial, doesn't matter which initial condition, the integral curve of V is in fact given by the restriction of this guy. And 3 is the main contribution of these two papers, that this guy is smooth. Schnetitsky did prove the existence and uniqueness of these maximal integral curve. He proved that the curves themselves are smooth, but he did not prove that the flow as a whole is smooth as a map on the subset of M cross R. So that's where the challenge was that we had to quite sweat on. And I have here something a little bit more technical. If M is locally compact, and for every point there exists an integral curve whose domain is the whole neighborhood of the origin in R. Then in fact, the flow domain is open in the product. This also is this is a little bit more general than something that Schnetitsky has already done. And the example at the top doesn't satisfy these assumptions because it is not locally compact. And I think my time is up. Maybe I'll just take one more minute to tell you what I was planning to do, which I'm not doing. One of them, I wanted to give you a sketch of the proof. As you can imagine, the main ingredients, just as you do for manifolds, is the classical theory for ODEs, the uniqueness of ODE solutions in Rn guarantees number one. The uniqueness of ODE solutions in Rn also guarantees number two. And the uniqueness of ODE solutions in Rn enables you to reduce 3 and 4 to just understanding the behavior. So it guarantees certain composition properties of the flow, and it reduces 3 and 4 to the behavior of the flow near the initial points. And then the existence and smoothness of ODEs in Rn, of ODE solutions in Rn, ODE solutions assuming that the vector field is smooth, that gives you what is still missing, which is the smoothness near the initial points, which guarantees everything. I was planning to also give you a little bit of a sample. It's pretty surprising basic pieces there that are, quite routine for manifolds, require more subtleties and more details and are more challenging in this setup, but we don't have time for that. I was planning to give a sample of that if no time. And one more thing, I put this, one more thing on. Yes, the first of these two papers I mentioned, so there's the earlier work of Schnetitsky. The first of the two papers I mentioned under embeddability, you can actually quote the theorem for manifolds to conclude the theorem for embeddable differential spaces. The second paper I'm talking about is more or less repeat the proof, not just quote the statement, but repeat the proof of what you do for manifolds. And this adapt it because many of the details become more complicated, but you can't just use the statement, you need to use the proof. So maybe at this point I should stop. Thank you.